to start us out, I just wanted to introduce the three of us who are going to be helping to run the workshop today. We're super excited. A lot of the people in this meeting are from the SWOT science team, as well as people from CryoCloud who wanted to have tutorials on SWOT and or to get a refresher. And yes, we're going to be starting out with an introduction to CryoCloud and working in the cloud and what that means. We can kind of wrap our head around that, and then getting into tutorials and more hands-on demo after that. So it's 2 hours long, and I'm Tasha Snow. I am
Folks.
the sorry, someone's not muted. Um, I'm Tasha Snow. I'm the research scientist at NASA Goddard and the University of Maryland. And I'm one of the co-leads for the SWOT Cryosphere working group. And yeah, I'm both a cryosphere and oceanographer, or cryosphere researcher and oceanographer. And yeah, do a lot of remote sensing. Very excited to work with you guys today. Joanna?
Yeah, and I'm Joanna Milstein. I'm a postdoc at Colorado School of Mines. I'm the other co-founder of CryoCloud alongside Tasha, and I also do a lot of remote sensing, mainly for ice mechanics. And then finally, our kind of third helper today is Zachary, who I'll let him introduce himself.
Hi, I'm Zachary. I'm a PhD student at the Colorado School of Mines, and I'm helped develop the tutorial that we're going to be looking at today to help with downloading SWOT data, streaming SWOT data in the cloud.
Cool. So yeah, you can reach out to any of us if you have any questions, work in the chat. If anyone hasn't done so, for everyone who's just joined, in the rights or in the chat, there is a link to the Getting Started survey that was also in emails. And if you could fill that out quickly, that'll help us to get you onto CrowdCloud quickly. So, Joanna, go ahead and take it away.
Okay, let me share this. Okay. Sorry, let's make sure this is full screen. Well, okay, we're just gonna walk through this. So yeah, you're all here to kind of learn about Earth's data science in the cloud and kind of onboarding all of you in this CryoCloud environment is going to just take a bit of a kind of mental shift. And so we'll walk through that before we actually introduce you to the interface and kind of the using SWOT data in the cloud. So right off the bat, we'll just kind of begin with this code of conduct. I won't read through it in full, but just to kind of put this out here, Tasha and I really believe in creating this welcoming environment where any question is on the table. And so we want to be respectful today of everyone's questions, kind of the many different experience levels that we're all coming at this with, and just try to create a really inclusive and welcoming environment for all of us to learn and do our science. So today, our learning objectives are kind of straightforward, where we want to understand the opportunities and challenges of working in a cloud environment, learn a bit about the general technical tools needed for working in the cloud, and then walk through CryoCloud itself and explore how to be useful for your research objectives, whether it be SWOT, other satellite data, kind of re-upping on your data engineering skills, and maybe you just really uh, use programming as a means to an end and you just want to make your life a little easier. So, this is entirely part of a kind of entirely kind of mental shift in how you're actually using your data, performing analysis, and sharing information. And so, first, before we get started, again, uh, we need to emphasize that you have access to hub.cryointhecloud.com. So, if you go to that website, um, and you can't, and nothing shows up that's linked to your GitHub account, you can't use the cloud, you can't access the cloud. So, um, if Tasha or Zachary could post in the chat, the getting started survey, if you haven't filled it out, and then the onboarding survey, we'll just pause really briefly for everyone to do this, so that we're kind of all on the same page. And if anyone's not, well, I'll just pause for 4 minutes or so to give everyone the chance to do this. if there's any kind of questions or if you think, yeah, we need to any sort of clarifying information, let us know. Tasha, does that sound good to do? Uh,
Yeah, let's take about like 6 or 7 minutes to fill out that onboarding survey. And then if you are getting a 404 error when you try and go to hub.cryoonthecloud.com, um, then then you haven't fully filled out the getting started survey and accepted the GitHub invitation from us yet. Um, Let me get the Joanna, you want to put the link for the onboarding survey into the chat? I'm grabbing people off of the.
sure. Here, this, um, only I could find the chat. This is like totally when the the computer skills break down on Zoom always. Um, but great. So also kind of useful information here is that if you filled out the survey yesterday and did not receive an invite, that invite will come in the form of a GitHub email, an email from GitHub to whatever email account is linked to your GitHub, or if you are directly on GitHub itself, you can accept the invitation. So, yep, if you can't find that, we'll make sure that you're on there, Mike.
Looks like we're pretty good on the getting started survey now.
Great. And I guess at this point, I'm seeing a lot of names in it who've accepted who are on this chat. If anyone is not on, if anyone is not able to access hub.cryoonthecloud.com, maybe just send Tasha a message or just post in the chat. But I'm seeing a lot of your names have it accepted. Lauren, let's see. So Laurent, your invitation is pending. So if you go to GitHub, if you log into the GitHub website and look at your notifications, you should have the option to accept that, and then you should be able to log in to CryoCloud. Mike and Luciana, these you as well have invitations pending. And for the award number, Khalil will you can leave that blank. You could just write SWOT workshop if need be. If you are funded by a NASA grant, we would love to know what that number is just for our reporting purposes. But if you're not sure what grant you're on, or you're not sure, or you don't have any NASA funding, just write down SWOT onboarding.
And as everyone like opens up and makes sure that they can log on to CryoCloud, don't click like start. So don't actually start the hub, and yeah, don't choose like we'll walk through how to do all of that. If you have already done that, um, go to File and scroll down to the second to last thing in that menu that says it starts with Hub. Go there, click Stop Server, and then log back out. You don't. We'll talk about specifically like what you need to put in to like before you like to start the CryoCloud itself. So we just want to make sure that you can log in when you push that orange button on hub.cryocloud.com right now. And I'll walk you through that in just a moment. So I think we're good for now. There's one more straggler we've got here. Just sent the last. Khalil just sent you an invite.
And
right.
Yeah, Tasha, will you explain where the invitation pending is?
The invitation pending, if you, I think the easiest way to find it is actually go to github.com/cryo in the cloud. And oops, shoot. I need to edit that.
And then let's see if you're on there.
There we go. Yeah, I just sent it out. So when you click on that, there will be a little banner at the top that says you've been invited. And I think I've invited everybody that has been signed up. So Joanna, let's go ahead and go, and then I'll work in the chat with anybody who has any issues still.
Okay, sounds good. This is yeah, kind of the classic part of any tutorial, right? Is that there will always be a little bit of technical kind of turbulence on the way to getting on board. So while Tasha troubleshoots anyone who's stuck, we're just gonna walk through this. This might be old hat to many of you, but this was very new to me when I started working in the cloud, and I really cannot emphasize enough, if there's one thing you all walk away from this with, using the cloud for remote sensing data analysis requires you to really shift your minds on how you're performing your analysis and sharing this data. And so instead of downloading data to begin your analysis, the cloud lets you bring compute. So that means instead of doing terabytes of analysis, or really gigabytes on your laptop, you can run your analysis right where the data already lives, hosted in the cloud. And that really kind of simplifies the time it takes to perform these things. This really adds up when you're doing, say, INSAR time series is something that I do. And so you're using tons of data, and there's many steps along the way. And so this will make things a lot quicker. This means also that we don't need to buy or maintain hardware, and you can scale something quite small to something really powerful that would require HPC otherwise. So we pay for things like data storage, hours of compute, and egress, which means the cost to move things out of the cloud. So that's kind of a new term to remember. But we are not paying for buying into an HPC, for IT support in that, racks, or kind of external hard drives. So it's a very flexible system. And then ultimately, it's accessible anywhere with an internet connection. Once you're onboarded onto the organization, all you need is to go to hub.cryonthecloud.com or whatever JupyterHub or interface to really begin your analysis. And so one of the big challenges to making this a totally seamless process is just that the data volume is expanding so rapidly, particularly for remote sensing data. SWOT alone is streaming an estimated 20 terabytes of data per day. That is massive and way too much for a kind of single researcher or even PI group to really to handle on their own. And so when you're talking about that much data, locally downloading from kind of a DAC, a NASA kind of storage facility, to your personal computer is just inefficient or nearly impossible. It's slow, storage intensive, and it's duplicative. So if I'm telling Zachary to perform an analysis on kind of the coast of Antarctica, and I've done it on my personal computer, and then I tell him to download that data as well, that's just really, it's quite redundant. And it also makes sharing and kind of real-time sharing this more challenging experience. And so that leads to really kind of frustrating reproducibility challenges along the way where we have different computing environments, we have different packages installed. And so as a scientist myself, scientist first, software second, spending more time on data wrangling and infrastructure is incredibly frustrating. When we all sign up to use this data, at least I'm speaking for all of us, but I really, when I signed up to use all this data, I did not want to become a cloud engineer. And along the way, when I found myself learning all these new things, I was getting frustrated. It really kind of hinders my progress to science. So one of the great things about what we're doing here by getting everything in the cloud is that we're unlocking this kind of new possibility where we can co-locate your compute, your analysis, and kind of processing and data. So we're not moving terabytes of data from a storage facility to your personal computer to your collaborator's laptop. Everything is in one place, and that creates this very kind of remarkably quick and frictionless environment. So, yeah, so we're bringing the analysis to the archive. And so these cloud resources are elastic, which means we can scale up or down depending on our problem. And that's really critical for earth sciences, where one day you might run a quick notebook, maybe from one scene or just looking at a pair of images. And that next day you want to launch a large parallel job. You've kind of done a proof of concept that you see a correlation in one area, and then you want to scale it to a continent or to a coastline. And so this is quite a common kind of phenomenon in our field of science, right? And we can also do with this cloud-based kind of research platform is collaborate quite easily. We can share workspaces and notebooks and reproducible environments, or just use the same managed environment. So that means that we're reducing the kind of weird ways you might need to pip install something or manage your Anaconda environments. That's no longer your problem, really, when dealing with collaborators. So that's an exciting way forward, at least uh, for those of us who've dealt with environment issues before, right? And then next, this lowers our cost of ownership. So right now, all of you have just signed on to CryoCloud, and you don't need to pay anything. We provide this resource to all of you and allow you to do data analysis on it without having to kind of contribute your own cloud credits or buy into a cluster maintenance. You're really only paying for what you use if you're using a ton of data. But what we found with all of the 800 users already on CryoCloud is that maybe only a percentage of our users are actually kind of requiring really truly massive, more than tens of dollars of storage. So that's quite exciting that we're talking about $1 a day for kind of bringing a PhD student into your lab to perform major data analysis. And then finally, the reproducibility of all this is just so essential to earth science, where these standardized environments that are maintained by cloud engineers ensure that we can reproduce data analysis pipelines just seamlessly. And that that's great. That's really in line with these kind of workflows that align with NASA's commitment to open and equitable science. And so FAIR principles for findable, accessible, interoperable, and reusable data are really built into the way these cloud platforms handle analysis through APIs, through standard formats, and persistent kind of metadata identifiers. And so this open science also has to be responsible, and this is where the CARE principles come in, where we're taking this was kind of developed from indigenous knowledge. thinking about collective benefit, the authority to control, responsibility, and ethics in our data practices. Moving to the cloud doesn't just make data easier to access, but it gives us this framework to respect kind of each other's work, respect the kind of land that we're working on, and ensure that there's equity in how we use and share this data. So that's kind of quite nice that built into all of this computing architecture is this useful way to be equitable and reproducible. And so what's great about our Jupyter Hub is that CryoCloud is managed by 2i2c, this nonprofit that manages our infrastructure, uptime, scaling, and security. And so this is a wonderful group of cloud engineers and research software engineers, many of whom are kind of original founders of the Jupyter ecosystem and have come from great open source organizations along the way. And so they help us as researchers avoid system admin overhead. So we don't need to deal with kind of the complicated compute issues, and they maintain kind of low latency updated uh, ma low latency maintenance of our hub for us. So this is great because we get to focus on our science instead of like patching servers. And so this external management is all using these kind of fair and care community best practices. It's entirely open and transparent. And so NASA can still retain oversight while we leverage this kind of specialized expertise and making sure that there's secure pipelines and give us, as researchers and scientists, user-friendly analysis portals. And so what's really great about this is that if we've got a problem, say I've got a problem, we can tell 2i2c about it and they'll fix it on the back end. What's nice is that if I'm having this problem, all the other users would be encountering this problem. So they'll fix it across the entire hub. This is just a really efficient way to tackle problems and debug issues within the hub. But we love working with 2i2c. It's a really fantastic organization, and they're quite active in our Slack. So if you join our Slack after today or during today, and you've got a problem, just as straightforward as loading a data product, you've got some 404 errors, you can post in Slack and they are quick to help us out, which is fantastic. And so once we get on board into the hub, this is a very familiar user-friendly gateway. It's browser-based, as I said earlier, so there's no installs. You just need your internet connection and a browser. CryoCloud is integrated with Python, R, Julia, and MATLAB. And so if you, in MATLAB, if you bring your own license, but what's great is that you can work in any of these programming languages you're already comfortable with. I can do my analysis in Python, make a bunch of figures, make a bunch of kind of data sets, and share them with a colleague who's only working in R. And this is just fantastic for kind of making your life a little bit easier, not having to learn new languages all the time. And it's quite scalable as well. So these workhorses of just GPUs we can work with, or if you're oftentimes just needing to do a little bit of analysis, you can decide how much compute you need. And you'll notice that when you log in, and Tasha will cover that more. But we have this very flexible infrastructure that allows you to choose your compute need. And then critically as well, we've got this consistent environment. You know that when you're logging on to CryoCloud, you're getting the same environment every time. We tell you about updates along the way when we've updated packages, and everything should work seamlessly. If there's an issue, it's resolved quickly by 2i2c, but things are centrally maintained, and that means that you can install your own packages and you can make your own environments. But at the baseline, you've got this flexible system that's designed for remote sensing data analysis. And finally, we've got training and onboarding like this, where we kind of spell out how this works for all of you. We take you through it, and we really just want to make sure that we hold hands along the way and give you the tools to work in the cloud successfully. And so finally, we got to talk cost, because this is often a question that we get. And local workflows often come with this hidden expense of kind of buying and replacing hardware, or hiring or buying into HPC at your university or institution, paying for power and kind of cooling. It depends on just how much data you have and need to work with. And so this cloud powers that it's pay as you go if you need to pay. Right now, again, we're providing this resource for free, but if you wanted to launch one of these on your own, it's a lot cheaper to work in the cloud. So because we're avoiding this duplicate downloads and redundant local storage across institutions, there's one central place, an AWS bucket, hosting all of our data. We're just paying for storage, hours of compute, and egress. Again, this outbound data transfer from the cloud. And so this is kind of a new way to think about things. When you log into CryoCloud, you are immediately we're paying for your time to use this compute, how much RAM you requested when you log in. We're paying for storage. If you're storing hundreds of gigabytes on CryoCloud, that becomes a problem. We try to ask that all of our users keep their data storage under 30 gigabytes. And what we found is that can be scary to some, but with SWOT, particularly with SWOT, you'll notice that a lot of things are streamable and you won't need to download much. A lot of people are scared and saying that 30 gigabytes is not enough. It almost always is. You'll be surprised when we kind of go through this mind shift of putting everything on the cloud. And what's great about this is there's just no hidden costs. It's really clear and transparent. And this consolidated cloud infrastructure is just lowering the total cost of ownership. All of us buying into this framework is a great way to kind of make this cheap and flexible system available to really anyone, which is awesome. And so what's great about here you can see that a SWOT subsys analysis of 10 terabytes locally would be like nearly impossible. It would take a PhD student a really long time to kind of figure out how to download that data on a university network where they're going to store it. But doing that in the cloud is a direct query from AWS, Amazon Web Services. I should have said that earlier. And the data is already hosted there. And the compute time, depending on the analysis, should be no more than tens of dollars for an entire like PhD project worth of data analysis. And this is great. It's faster, it's cheaper, it's on the back end maintained by software engineers. So you as a scientist don't really need to deal with kind of the technical hiccups. You can really just do your science. And next, this is kind of perhaps straightforward to many of us, but these browser-based tools are really lowering the entry barrier for earth science students. And so we're not asking that everyone needs to come in with these advanced computing skills. And so students, early career researchers can train in these interfaces that are comfortable without needing to know a ton about the back-end cloud infrastructure. And so in developing these flexible cloud skills, you'll realize that they're quite portable across academia, industry, government. All of us are working on different kind of subject matter ideas, but with the same computing tools. And so we're taking principles from research software engineering, learning best practices that are coming from software engineering into science. And this is just a great way to make sure that us as scientists are learning ways to share our kind of computational information in a way that makes sense across fields. And so finally, we're really, what we're trying to kind of do here is enable shared scalable science from SWOT and beyond. As I said earlier, 20 terabytes a day of high resolution data is just not manageable for a single person. NISAR, which launched earlier this year, is expecting to quadruple that with 80 terabytes a day. And so the amount of data is expanding kind of exponentially, and keeping up with that is really exciting from a science point of view and daunting from a computational point of view. And so what CryoCloud is doing is trying to make this easier, and so we can embrace the exciting part of this whole thing. If you today walk away from this tutorial learning how to kind of use SWOT data in the cloud, that is a portable skill across other satellite remote sensing missions, NISAR, PACE, which launched again last year, the entire history of the Landsat mission. All of the data is catching up to the cloud, which is exciting. So SWOT is kind of Tasha and I have been really excited about SWOT because the kind of data architecture is built for the cloud in many ways, much more so than other missions. And so you all as SWOT scientists, or just as interested scientists, are really going to be able to lean on the seamless cloud integration of having everything hosted in one place and having your analysis not need to move from external to local back to external. And so this common infrastructure of the cloud, where we have the same tools, the same workflows, and different missions means that you can just actually work across data sets and perform data fusion for legitimately cross-disciplinary work. We're quite excited about this. I've seen this happen uh, for many research projects and just think that the potential here is completely unrealized and there's so much exciting stuff to do. So now that you understand really finally that there's a lot of exciting things to do in the cloud, but we have to think differently about our costs. You can keep the cost stuff in the back of your mind, but we'll move into Tasha's portion of this tutorial, and we're one step closer to getting you on the hub. Tasha, do you want to share so you can drive, or I
Yeah.
can just okay, cool.
All right, can everyone see that? Cool. Kind of tagging on to what Joanna just said, part of like what it is to be making this cheaper is like a lot of people won't choose to use the cloud for 100% of their work, and we're finding that most people don't. I use it for 100% of my work. And because I can access it from my cell phone or a tablet or something like that, and it's literally costing us like $180 a year for people, it's way cheaper for me to just buy a tablet and do my work from there than buying a powerful laptop. So that's it puts the personal cost a lot less, to a lot cheaper than what we do currently for the most part when we're not using the cloud. So as we have this like cloud space, new community models, computing models are kind of needed. And that's where CryoCloud's kind of history comes in. I'll give you a very brief background on that. CryoCloud originated to support the NASA ISA-2 science team. We were in a science team meeting in 2022, and the science team was talking about the fact that it was really rough actually working in the cloud at that point. They were finding that standing up usable infrastructure was prohibitively challenging. There's non-intuitive pricing structures, documentation, and computing options, which none of us will have to know about. But if you go onto AWS, it's extremely confusing to try and set up anything. You have no idea what you're paying for. People were finding it was costly to use because their institutions didn't know how to set up the infrastructure, and they were keeping things open that were very expensive. And so you weren't getting any computing done for like $4,000 in a month. And they were also finding that it wasn't obviously more collaborative or faster. And a lot of us that had used JupyterHub set up by 2i2c had been like, this is not how the cloud needs to be. So what we decided to do was to pair up with partner with 2i2c to build a cloud computing platform with bumpers. And it's a simple cost-effective managed cloud environment for transitioning and training new users in the cloud and for developing community best practices. So we're trying to figure out ways, since no one's really done this before, we're all like, Jupyter hubs are new, working in the cloud is new. We need to figure out the best way to do this to be cheap. So we're doing a lot of that work. You can visit cryointhecloud.com. That's where our Jupyter book is located, and our hub. And so if you visit our Jupyter hub or our Jupyter book, it has all of our training and recordings and tutorials and stuff, all of our best practices. That's at book@cryointhecloud.com. I'll show you in a moment. And then our hub looks like this when you open it. And having a Jupyter hub is meant to give you a unified experience between your laptop, if you're using the HPC in the cloud. So it should look the same. So a Jupyter hub is the same as Jupyter Lab on a computer, if any of you have used that. It has a lot of the tools you need baked in. So you can have a full terminal window to do your command line work. You can do your file management. That looks really similar. You can open markdown files both in
bigger. It's just only half your screen. Yeah.
Oh, interesting. All right. Let me do.
Awesome.
I forgot that it was not. Yeah, there we go. All right. So the the markdown with preview, you can both work in the markdown and look at the preview. There's lots of cool tools for doing that. We have launchers with all of the different tools. And lots of different ways of looking at your data that are built in that might even be nicer than your actual computer. There's also been a virtual Linux desktop where you can work in QGIS. So when you produce an image in the cloud, in CryoCloud, you can go and take it over and look at it in QGIS. We have SyncThing, which is helpful for moving data. And I'll show you all of these in the cloud in just a moment. We also give you a versatile choice of computer language and server size. We have some built-in things. You can bring your own environment and you can build your own environment. And I'll walk through that in a moment. And then you can choose different like amounts of resources that you need for the day that you're working. And all together, we can basically, no matter what sort of data set you're working with, especially at NASA, we can bring those all together in one place, stream them really easily. A lot of the science team members from those missions are on CryoCloud. We also have the tool developers from a lot of the tools that you'd be using from Earth Access and X-Ray. A lot of these people are already on CryoCloud, and putting that all together in science, like Joanna's kind of talked about, we have a lot of different kinds of users, data producers, tool developers in one space. And that, especially having everyone in one Slack space, we can get feedback really quickly. So you can ask questions, debug. And when you ask questions, the tool developers get to see where people are having problems and build their tools to better suit your needs. So it's great if you're using our Slack. That actually helps to improve all of these tools a lot too. And so you can hopefully collaborate much more easily too. So that's kind of the beauty of having both a Slack and a JupyterHub paired together. So now I'm going to take you on a test drive of CryoCloud. For anyone who had already logged in, I'm going to ask you, let's go to hub.cryonthecloud.com. If you are here it says login, and then you'll get this thing that asks you to give permission. Yeah, go ahead and authorize to I2C. You have to do that to be able to access the cloud here. And then if you went beyond this, can you go to file? If you're already on CryoCloud, go to file, hub control panel or whatever, it's the second thing from the bottom, and then press stop server. And then when that red button goes away, press log out and then do all this again. I'm going to walk you through right now what you can kind of choose. And some of these tools are brand spanking new. Oh, you want it bigger?
And make this like bigger. Yeah, it's just the tiny.
Thank you.
Yeah. Can everyone see okay? Just put in the chat if you're, oh, perfect.
Unable.
That is, yeah.
Cool. Maybe I can make this even. My screen's pretty big, so I forget. There we go. Okay, so when you open CryoCloud, you have these different options. These are different environments. We maintain different environments for our users that have all of the cool tools integrated into it. So when you build, it's called an image. It has an environment which has like all of your Python packages and things like that. But it also has all of the tools integrated. So like if you want VS Code and things like that, it also has to be in it. We maintain one that has a lot of stuff in it in the Python image. We also have an R image. MATLAB, you need to bring your own license, but we have MATLAB on CryoCloud. Another thing that you can do is you can go to other, and this allows you to bring someone else's. And so one thing we can do is if we go to book.cryointhecloud.com, we have some best practices, and this kind of describes being able to use other. And one thing that you can do is you would type in a tag. So it walks you through like what the tags are and how to create these. But like we have a CryoCloud tag for all of our images, and every version gets a new tag. And so if we create a new version of the CryoCloud environment and it doesn't work for you, you can go back to old ones by looking at our account here that is listed. And so this is what a tag looks like. And you would go in here, please don't do this at the moment, but this is how you do this. You just type it in here, and then you choose your resources that you want. So that's how you use bring your own. So one that's already built. If you want to bring one that's new that you've never done before, you can go in here and you can basically use any GitHub repository that has an environment.yaml file. And so I've built basically here, I'll copy this into the chat. You don't need to access this right now. But this is bare minimum environment that you need to use. And then you add your Python package. This is just for Python. You add your Python packages on top of it. This is the YAML file here. So all it has is like Conda Forge, JupyterLab, Mist Markdown is how we visualize a lot of the Markdown, and then JupyterLab Mist. And so what I can do is I can go to whichever repository I put my environment YAML into that has those minimum requirements in it. I take this HTTPS, copy this, and you can revisit this recording, so don't worry about copying this down. Copy that, and then I put it into here. It says build your own, and then I can say build image. So it'll look for the environment YAML in that repository, and it'll build it. I already built this yesterday, and what's cool is because it's already been built, it knows it's already been built and it doesn't rebuild it again. So it says, cool, it's ready for you. Now you can just press start. So we're not going to do that here because we're not using that environment, but this is how you use build your own image. So if you really want something specified to your use case, you can do that. And it's much faster to run a smaller environment. The problem is it may take 30 minutes to an hour to build that. This one is minimum, so it only takes like 30 seconds or something, but it can take a long time to build it. But also it may not have all the like bells and whistles that CryoCloud has, because like the virtual desktop needs to be added into that environment and things like that. So you have to be aware that if you build your own, it might be a little bit more bare bones than what CryoCloud comes with. But what we're going to do now is we're going to click this Python image. This is what we're going to use today. And we have a lot of different resources available to us, and we'll choose the smallest one that we need for today, which is actually 7 gigabytes. So I've already run the tutorials. I can show you how we look at the memory, but keeping track of memory is really important because we want to use as few resources as possible to save CryoCloud money, because we're all in this shared like environment where we're sharing costs. And while CryoCloud provides everything for free, we want to keep this tenable so that we can run CryoCloud as long as possible for as cheaply as possible. So the idea is that if you run a notebook and you see how much memory it uses, you want to use the minimum amount here to minimize the cost. So we just need 7 gigabytes here, and you can press start. So this is opening up the container image that we have, our Python environment. The Python image is kind of large, so sometimes it can take a little bit more time than this. But this is what it looks like when you open CryoCloud. And just so you know, for this demo, if you don't want to go through yourself and find things, if you don't want to go through the tutorials, it's totally fine to just watch. All of these things are going to be available. The recording's available. So if it helps you to click through things, you can, but if you fall behind, don't worry about it. You can sit back and watch if you prefer. So the first thing I want to show you here is the kind of your file management system, which is over here. It's on this folder. Here, you'll just see there's a desktop, shared, and shared public. The main things I want to note here is shared is a place where some of the admins can place data. You cannot write anything to this, but a lot of the SWOT data is going to be here. You can find that. Like I said, you can't write anything. So everything there is shared, but users can't change it. Shared public is a place where things can be changed. So if you end up deleting a bunch of stuff off of your workflow, all of us have the ability to delete any of these files and to write to them and change them. Please don't touch anyone's but your own, because if you do, it could potentially wipe out someone's work. So these are places where people are sharing things with their entire group. The thing to note about shared public is if you do share things here, please make sure it's not the only copy and it can't be reproduced very quickly, because there is a slight risk. It has happened once on CryoCloud in 3 years. So it's not it's pretty infrequent that it happens, but if you put things here, make sure that it's not the only copy, and it's not going to take you years to reproduce it. But this is a place where you can share with each other. So that's the file extension area. Pressing this plus button gives you this launcher that's right here. You can open a notebook. So I'll just discard that. You can open a Python notebook in this image. This is where you'd see RStudio if you opened up R, or you'd see MATLAB. We have a virtual desktop. This opens up basically what you would have on your own desktop. And so like I can open up QGIS here to visualize things. SyncThing, I'm not going to go through that. There's lots of documentation online for how to work with SyncThing, but I don't think a lot of people have been using it. We have VS Code here. The console is a nice place where you can do like work. If you want to test things line by line, you can use the console. You can move these screens around so you can view them a little bit more differently. So you can like type things in kind of one by one like you would in Spider, or you can run these notebooks in line. So you have the option to do both. You can open up Terminal, which is your command line, and run your command line like you would on your computer. Create text files, markdown files, if you want just .py, things like that. All of that is from this little button here. You can add a new folder, upload data. So there's two ways to upload like data from on your local computer. You can either upload it here, or if I were to take my like file, my normal browser, I could just drop it in here. If you have really big files, note that it's going to take a very long time for them to upload here. So we have an S3 bucket for you to be able to use, and instructions on our Jupyter book on how to use it. They're in the how-tos, and using the CryoCloud S3 bucket, you can do this work from your, you can send data into the cloud really quickly using S3 buckets. These are just like temporary and not meant to be storing a lot of data. But if you have something big, we do actually have one that is not Scratch, that isn't temporary. So talk to us about it. If you find out you have like a file that's one gigabyte or something like that, you'd want to use that. So that's uploading data. Going down this left-hand side here, these are all of your open tabs. Kernels are basically like things that are using resources. So these are like, I open this untitled Python notebook and it's technically still using resources. So that's why it has this green button next to it. I can shut down that kernel and the memory that that's using will go away. So that green button went away. So that's using memory while it's still open. And you can see down here the mem. This is, we signed up to be able to use 7 gigabytes of memory, and we're using less than a gigabyte at the moment. That's how you keep track of the memory. This will turn red when you start to approach those limits. And when it turns red, and then goes over, the kernel will shut down. So it won't like crash anything crazy, but you will lose all the variables and like all the computing that you've already done on that notebook and have to start back over. So it is important to like keep track of that. And it is a nuisance if you have something that's writing right on the edge. You may as well just use one size larger for your compute. And you can see terminals are listed there too. Dask is a tool used for parallelization. We recommend using that. We have some tutorials on our Jupyter book that you can use to figure out how to use dashboards. This shows you how the resources are being allocated when you parallelize. A way to interface with GitHub. There are a number of ways to do that in CryoCloud, so you can use this. This is a nice place for looking at headings in, say, like a Jupyter notebook. So when we use a Jupyter notebook, we have 2 different kinds of cells that we can have. There's code cells, like you would type your normal Python into, or R or whatever, or there's Markdown. And Markdown you can use for writing titles and things like that. Or if we use 2 here, let's make this in a markdown file. We can do subtitle, and the two hashtags kind of change, and you can change the size, and you can see that comes out in our outline here. So I can navigate. If you're like me, I put a million lines of code into one notebook, and then I have to scroll down to the bottom. You can use this title system to be able to do that really easily. We have an extension ability. There's a lot of extensions in Jupyter that we don't have installed. If you want to use those, you can come in here and search for them. One thing that we like to use is collaboration, Jupyter collaboration. That's one that allows you to do co-coding, kind of like you would in a Google Doc. And what you would do if you want to load this extension is you would click install. It would say it's installed. You need to refresh your environment. And then you come up here, press refresh for this page, and then it'll be installed. So that's how you install extensions. And then here we have Jupyter AI. So you can work with AI models here. And you can ask it questions. There's different like things that you can add in here, like ChatGPT and things. I won't go through exactly how to open this because they have lots of good tutorials online for how to use it. But this is a tool that we have baked into this. Over on the right-hand side, there's just some like advanced things about the metadata for the notebook that you're in. Kernel usage and memory is again stored here, so you can see it broken down more here if you need to. And if you do any like debugging, you can use that there. In a Jupyter notebook, if you're not familiar, you can save, copy, all of these things highlight really easily. The one thing to take note of is this square. If you want to stop what you are running because it's running or it's broken or something, you can stop that there. And you can also do that from up here. I'll show you in a moment. And then changing the cells, like I noted before. Markdown's really nice for like, hey, this is the calculation that I use. This is the equation that I use. This is the description, and then writing the code. Up here in the top, we have help settings. One thing I wanted to point out here is theme, so I can change it to a dark theme if you like changing colors and things like that. Tabs. A lot of these are redundant to other things that we have elsewhere. Another Git way to interact. A nice one that I use a lot here, interrupting or shutting down the kernel. If you want to like stop and erase everything, you can use restart kernel or shut down if like something gets stuck. Interrupt kernel is the same as pressing that square button. Run, I don't really use. All of these are pretty self-explanatory in view. And then file. One of the main things that's really important for CryoCloud. One of the bumpers that we provide here is that the cloud shuts down after 90 minutes if it isn't in use. So if you are writing something and you walk away and forget about it, it will shut down. So that's really important to know. There are ways for keeping it longer if you expect your analysis to run a lot longer. But in general, we don't use those because that can mean that you could accidentally leave this open and spend money indefinitely, right? Because the amount of time we spend computing is how we get charged for CryoCloud. So this shuts down after 90 minutes if you're not using it. So if your mouse isn't moving around. If you just go to log out here, then this will not shut down the server. You will be able to open it back to exactly where you were. But that means that it will stay open for 90 minutes. So to save us money, the best practice for shutting down your JupyterHub when you're done is to go into that hub control panel, press stop my server, and then once this button goes away, go ahead and log out. And that's how you'll log out. And once you're done with that, make sure to close the tabs. If something gets weird, like you accidentally crash something or something's been like pip installed that you don't want, it can create these weird things like you would have your own system glitch. And by getting rid of these tabs, it like helps it to clear the system. So I recommend every single time, stop my server, log out, and then close the tabs. And then if you want to open a new server, open a new tab. If you want to start over fresh or use a new image or whatever it is, that's what I recommend. So that brings us back to where we were in here, I wanted to just do a few general housekeeping things before we jump into the hands-on parts. So for housekeeping, please try to keep it to less than 10 gigabytes of data storage. And we will start to notify you if it gets up above 30. It's $90 a month to store 2 terabytes of data. So just to give you an idea of how much it costs. So that's a huge shift in using your laptop versus using the cloud. And like, if there's something big, pull it off the cloud if you don't need it immediately. If you need it and you're actively using it, then keep it there. But if you're gonna walk away and not touch like your data for like a month or two, the best practice is to move it off because we're paying for it the entire time it's sitting there. And we can work with you to find bigger storage options if you feel restricted by this 10 gigabytes. Temporarily storing more than that is fine for like a few days, but definitely like delete it off quickly if you can. When deleting things, make sure to leave shared public alone. Pip installs. So if you do a pip install to kind of facilitate reproducibility, those only last for that session. So you have to pip install each time, and I'll show you the best practice for that. But using percent pip install pack, like whatever your package is, in the top cell of your notebooks will help you to remember to do that. And for the next person to do the same exact thing and reproduce the exact same thing when they use your notebook in the same environment. If a lot of people are using the same package, we will add that to the environment. And I'm actually building a environment for SWOT. So I'll pass that around to everybody once we have that built. It's being built here at our github.com/cryo in the cloud. If you go to our repositories, the SWOT Python image is what I'm building for SWOT. And that's in progress, but any additions that you think need to be made to that, you can let me know and we'll add that. And then that way that'll be in the drop down, like automatically available for people. That's not what I wanted. And last but not least, again, make sure to use that file, hub control panel, and stop server before you log out. Troubleshooting, we've already mentioned this. Use on our Slack, use hub user questions to ask any questions. You can add GitHub issues if there's an issue in our Jupyter book or in our image, like if something's broken, if things are scrolling poorly, like it may have been that we added something and it broke something else. So let us know if you have any problems. And then you can always email our CryoCloud team. Make sure that if you are using CryoCloud when you publish, to use our citation. This is our DOI. Make sure to acknowledge us. We can better like make a case for keeping CryoCloud going when we have more people citing us and acknowledging us. And then also message us on Slack and let us know when you have another paper that you've just submitted or that you've published that you've used CryoCloud for. And that will help us. We'll put that into our Slack and be able to celebrate that and keep track of it. And that helps us know how much impact we're having. But yeah, in general, CryoCloud is part of your methods and how you're doing this work. So it's important to list it in your methods and acknowledge us either way for reproducibility. And then here's a cheat sheet for all of the CryoCloud things that we have, all the different websites. One thing to note that I haven't gone to yet, our CryoCloud Zenodo community has all of our PowerPoints that we've like presented. A lot of like our Jupyter book is stored there. A lot of things are held there. So if you want to contribute to it or find something, it might be there. I won't go through a lot of this. There's cool functionality in JupyterHub and Lab, and I'll show you in just a moment. Magic is something that's different, magic commands that add functionality. I'll show you in a moment. Matplotlib widget does interactive plotting. Percent time helps you time the cell you're running. So there's a lot of these cool functionalities. And then if you want to interact with the command line from your notebook, you can put an exclamation point before it. And then there are shortcuts in Jupyter. Like if you want to run a cell, I just run command return or shift return if you want to move to the next cell. So there's lots of these different kinds of shortcuts. And if you want to efficiently load large files into CryoCloud, this is the way that you would do that from your laptop to put that into that S3 bucket. S3 is cheaper storage than what's on specifically on the CryoCloud like file explorer. So and it allows for larger files. So you can go ahead and use this system. So from here, let's get started on the demo part that you're going to actually do some hands-on work. So for this demo, we're going to first clone the CryoCloud website, our Jupyter book, all the tutorials, things like that. And Joanna, do you want to put that into the link there? The other way that you can find this is if you go to like CryoCloud and GitHub, the CryoCloud repository. If you click on code here and just copy this HTTPS, then we can go into CryoCloud. So everyone hopefully has that copied. I'm gonna open up my terminal, and you can see we're in Joby, and that's the home directory. So I'll type in git clone and then paste that HTTPS. So we're going to clone this repository. That's doing that really quickly here. And you can see the CryoCloud folder just popped up. So that's going to have all of our demo information, a lot of the tutorials we're going to show. So I'll give you a second to do that. And if you have any problems, just go ahead and send it up in the chat. I'm going to give you about 1 more minute. Yeah. So in here, it's just git clone and pasting that file name. Joanna has copied or Mike copied the Git repository name there. That's the HTTPS. Just copy that out of there and then just type git clone before copying that in. So git clone and then the HTTPS URL. Thanks, Mike. All right, so now that we have that, let's go into Cryo in the Cloud website. We'll click on book. And if you fall behind, don't worry about this. Like I said, you don't necessarily have to keep up here, but this is where we're going to go to. We're going to go to the tutorials here. So this is where you should be your go-to if you want any of the tutorials from CryoCloud. And then we're going to look at the CryoCloud demo really quickly from this tutorials. And you can see up here the path that we're going through. So it was CryoCloud website, book, tutorials, and now we're going to go into the CryoCloud demo. So this is going to walk through what we basically just already did. You can find the link for this slideshow that we just showed. A lot of the information about opening things, like all of that is right here. And the information about how to stop your server and whatever. So you can look through this again if you'd like. Going back to tutorials up here, you can click back. We're going to go to the SWOT HR tutorial in just a moment, but one thing I wanted to note, so you can see really easily, there are different ways to look at data in CryoCloud. This is, we have a CSV here. This opens up really nicely so you can see it in block format. You can't edit it here though. So if you were to go and say open with, the viewer is what we were just looking at. The editor is different. This is what you would look like. It would look like if you open this up on your computer. So you can actually go in and edit those columns and things like that in your data. You can also do things with GeoJSON files. So this is a GeoJSON file. Normally when you open it up, this is again the viewer. If you were to open it with the editor, this looks like what you would open it up like doing it on your computer. So this is what the actual data looks like. But what's nice is we have some integrated tools that make it possible to interact with that GeoJSON file really nicely in CryoCloud. There's also stuff for HGF5 and NetCDF files. So if you have an image that's in H5 or NetCDF, you can click on that. And then there's a viewer. think I actually have any of those downloaded. So actually I do. I'll show you here really quickly. Shared public, but there's something in like paste. Well, maybe not. I'll show that later if we come across it. So now that we're in tutorials, go ahead to SWOT HR, and we're going to start the first tutorial for CryoCloud, which is the SWOT HR access. So that'll pop up. Again, if you can't keep up, like if you don't keep up, that's totally fine. You don't need to run through these. I'm going to run through this fairly quickly because this is data search and access. It's fairly simple, but you can come back and get more information if you want later. I do want to acknowledge that PODAC and NSIDC, which are NASA data centers, had tutorials that I've borrowed some information from. So you will see that within here, and I want to acknowledge them. What we'll learn in this tutorial is how to find and stream SWOT data directly into memory, and how to inspect those variables and visualize it. So this is basics for anybody who hasn't done this. I know a lot of people have already done this, so you can sit back if you've already used Earth Access a lot. We're going to use Earth Access for this. Note for beginners, again, streaming means not having to download directly into memory. What we'll do is we'll do a quick sign in to Earth Data Login. If you don't have the login for Earth Data, like your username and password, that's okay. You won't be able to run the tutorials here, but you can go click here and register for that right now if you want to. We're going to search for that raster data, open results in Earth Access, and then visualize it. And of course, this is meant for anybody who needs it. So SWOT background, the Surface Water and Ocean Topography mission run by NASA and CNES. All of the data is in the cloud. And the next tutorial we're going to do is to use this information we've built here, how to access SWOT, and compare SWOT HR data, high resolution data, to ISAT-2 over Bok ice shelf in the Antarctic Peninsula, and show you how to do some of that comparison. We're going to use, so HR is high resolution. There's an LR data, which is low resolution. It can have up to 10-meter spatial resolution. This product is 100-meter resolution that we're going to work with. And it's the water mask raster image. That's just the product that it comes in. So that's what this looks like here. And if you want more information about this product and SWOT, you can click on this link to check it out. We'll start by running this. I'm going to press Command Return or Shift Return. Shift Return is going to do this. It's going to move us to the next cell. If I do Command Return, this is on a Mac, so it's slightly different on a Windows machine. But if I use Command Return, I just stay there. I don't move to the next one. And you'll notice that Matplotlib widget, and I'll show you what that gives us later on. But we'll do that read-in. Here we're going to use the Earth Data Login and just run this. If you don't have a NetCDF, it's going, like I don't here, it's going to ask you to use your username, and I hope that's it. Let me get that really quickly. Small glitch. Not what I meant. Here and copy. So I found that. I'll run it again. Do snow 3 and run. There's my password. It's this message doesn't pop up, so it's worked. And Earth Access uses the common metadata repository from NASA in the background. Earth Data Search does this as well, if you're familiar. So we can search data sets, and we can talk, there's advanced ways to search. You can check that out if you want to later. But we'll just do a search really quickly here for SWOT. So We say Earth data, Earth access search data sets, keyword SWOT. We're looking for anything that has SWOT. Cloud hosted, true. Everything for SWOT is in the cloud. And then version D, this is the most recent version. If you want a different version, you can type it in there or just delete this to get all of it. So if we run this, we end up getting 35 data sets. And we can get a summary for each by running this code here. So I'm just running this for the first 5 data sets. But what it'll show here is, cloud info region US West. So CryoCloud is run on Amazon Web Services US West 2 region. And so what this is telling us is this is the same region. In the cloud, there's 3 things, Joanna mentioned this before, that we pay for: the hours that we use at compute and the size of the compute that we use. So if we use a large computer, it's way more money than if we use a small one. We pay for data storage. And 3, we pay for egress. And egress means taking data out of one cloud region and putting it into another one. So that could be from Amazon to Google. It could be from Amazon US West 2 to Amazon US West 1. So to save money and not get charged for every file we're moving, it's ideal to be in the same place where we're crunching a ton of data from. So we are in the same place as Amazon. So that's good to note here. We're in the same place. You can get information about S3 credentials. So this is all like things that happen in the background. There's a lot of credentials here that are used to be able to access that data. Concept ID, this is individual to each of the data products and their versions. File format, get data, you can get information about each of these data sets. If you click on this, it'll take you to the description for it. And then the short name. This is the main thing that we normally know about: SWOT, L2, LR, SSH. This is like normally what we use for searching for things and working in Earth access, and then version. So you can do this for all of these. And the main short names that we have here for SWOT are listed. These are all version D, but you can replace the D here at the end with 2.0 to get version C if you're interested. Some data is not yet produced in D, which is why I mentioned that. Today we'll be working with the HR raster data. Any tutorials that I know of that are associated with these data sets, I've listed here on the right-hand side. You can click on them, and this is going to take you to the PODAC tutorial for this. If you want to have other tutorials for working in the cloud, PODAC has a bunch of them for working with SWOT. There's all these different data sets, and then there's a hydrology and oceanography products tutorial there as well. You can click on those links. If you just want to see the short names for all of those collections, I'm just adding this little keyword thing here, and you can see all the ones that were listed in the top 5. So now we want to search for SWOT data using spatial and temporal filters. So we've created a bounding box for the area over Buck. And then we now have the short name that we want. We use the temporal range from May 1st to June 30th and add in that bounding box. And we get 4 granules from that. And once we get those granules, we can run this to really nicely look at what that data is and where it looks, where it lives. So this would normally pop up with a little tab, but SWOTs are broken. It seems like a little thumbnail picture showing you what it looks like. If you click on this, it'll take you to download the data. I don't recommend doing that. You'll have to log in first, but then it gives you a little information about each of those. That's just a nice way to look at it. And then you can open and load and display the data. At Earth Access open with those results that we just had opens this into an object. And that's really important because working in the cloud kind of requires, thinking of things as objects rather than files. And that is, so AWS uses like cloud storage systems. So all the data that we're finding in the cloud is in these like object files. And then things like HDF5 libraries and the things that we're used to working with want like a file system, like a file. So this like open makes that transition for the cloud. So then you can open it into this. We're opening it into Xarray here. into a data set. And what's really nice is that as we visualize that X array, we can see the different dimensions, X and Y. These are the different coordinates that are there. These are the actual, like if we were to type in, ask for those coordinates, those are the numbers. And we can get information about each of those, the units, things like that. This is if you aren't familiar with working with X-array. All the data variables are here and information about them. So longitude, longitude is in degrees east, and it ranges from negative 130 to, or 180 to positive 180. So we can find out all that information really nicely. And none of this data has actually been completely written. It's lazy loaded. So until you actually are doing computations on it, we aren't sucking up very much memory. And then we want to work with a large time series. We want to read in a bunch at the same time. We want them to serialize based on their timestamp. And so we can use something like the file name, which is right here. This is what the file name is. There's a date here for when that file was taken. In Xarray, you can use this thing called preprocess, where you can add things like a time dimension. And that's what we do here. We grab this file name, grab the timestamp out of the file name, and run that preprocess function here. And so now Xarray is going to open MF dataset. That's going to open all 4 of these and add the time dimension. And once that's open, we will be able to look at specifically ds.time.values and see that all of these are the 4 different like time dimensions that we have. So this is still running. It takes a second to go. And then we will plot all of that using HVplot. So if anyone's familiar with HVplot, it's a really, really nice interactive way of visualizing Xarray especially. So yeah, now you see we have that extra time dimension. And this is opening in just a second. Does anyone have any questions from this tutorial? Because we're finishing up this tutorial right now. I don't see anything. Cool. Everyone's keeping up. So this is HVplot. We can move this around. This is something that Matplotlib widgets helps with, is with our different plots, we can move things around. We can zoom in on this. So this is a height from one of the dates, and you can see this slider over here. It'll take us to the next image in just a second. It takes a second to load and open it. And so you can scroll through the different images from SWOT really easily. It's taking a little longer than it usually does. There it is. And so we can interact with each one if you want to like scroll through. So that's the access tutorial. So let's go over here. I'm going to open up the tutorials, the other tutorials, which right here is the SWOT HR with iset2 file, if you're following along. And we'll go through the second tutorial. Zach was the main person who wrote a lot of this, so he's going to help to answer a lot of the questions. But we're going to go through how to compare SWOT HR elevations to iset2 elevations. We're going to first start by plotting HR and LR coverage over Antarctica and show you how to do this from the orbit files SWOT, so that you can see where we have data that might overlap with iset2. And then we're going to grab the data from SWOT and iset2 and apply geophysical corrections to be able to compare them. So the first few blocks here are, one of them is kind of lengthy. So I'm going to go through and I'm going to run all the gray cells here and then walk you through the actual tutorial. So the gray cells are the code cells. I'm going to run all of these so that it's done by the time we get down to the bottom. And stop at compare SWOT. So the learning objectives are to plot the availability of LR and HR data over Antarctica, then grab data from iset2 land ice elevations, which is the ATL06 product, and compare them to SWOT HR. correct for different geophysical corrections, and then advect the ice between acquisitions. So we're doing this over an ice shelf. The ice moves. If there's several weeks between an ICE2 acquisition and a SWOT acquisition, then we need to advect the ice to be able to make that comparable because the ice has moved. And then we'll plot the comparison after that. We'll start by visualizing, and this is going to be like kind of a no-brainer. These are the different data sets we're going to use, and we're going to reproject them. And so if you want to access those data sets, the links are here, descriptions for them are here. The HR nominal mask is the mask over the northern, or the mask taken during Northern Hemisphere summer, so from March to November. And there's also a seasonal one that's from the other 3 months that we won't show here. And then LR, that is taken all of the time. It's the full coverage of SWOT. That data is found on Aviso and Kness. And then we'll open the Scripps Antarctic Polygon, which is the outline of Antarctica and the ice shelves. If you want to learn more about opening KML and KMZ files, which are these up here, then you can do that there. So we're reading in the different packages and reading in the path to where we want all of the data and where it's going to be stored. As I showed you before, we're using SWOT, the shared folder, and SWOT data as like the primary place where we're storing this data. You cannot write to this. So if you want to end up downloading something or writing something, you will need to use a different folder instead of shared. The nice thing we're using here is path. That library allows us to really nicely connect like a higher path area. So this like main data area, and then to add, different pieces to it and file names so that you can access them really nicely. The source URLs for both the nominal and seasonal mask and LR are here that can be used for downloading. Basically throughout this, if there's anything that takes a long time to open and stream, or if we have to manually download it, we've already done it for you. But the code is here. So the code will check to see if it's available, and if not, apply it. And so best practices are written into this. If it's really nice if we're all doing this and it takes 5 minutes to open and stream something, to create one copy for everybody, and then not everyone has to do it. It's much faster. But in general, we recommend streaming as much as possible and not downloading and keeping things. One copy is fine for us to do. So that's how we're going to do this and keep that shared. And then this is the Bach ice shelf area. We're going to read in some helper functions. These aren't super critical to really understand. They're just little things for helping to download HTTP files. The ensure scripts is going to check if we have that file, and then if not, fetch it. Read all KML layers. That's just for opening those KML and KMZ data layers from HR and from the LR file, and then save it. So that's what's here. And then first, we're going to start by reading in the Antarctic base map. We've already downloaded it for you, but this, like I said, has codes to be able to do it for you if you don't have it for some reason, or on a different computer. Then we'll reproject and grab out the grounded ice and ice shelves separately so we can plot them more easily. Opening the SWOT HR coverage, it's a big file. It's what, 500 and something orbit tracks. And so we don't want our plotting mechanism to have to deal with all of that. So we just cut it down to 60 degrees south. It makes the file a lot smaller, and we can read that in really fast. We don't do that here. The code to do that, to open it temporarily, cut it down to 60 degrees south. And then we grab only the swath data. We get rid of the nadir tracks. You can change that if you want to look at the nadir tracks as well. That takes 23 minutes to do that. It's really slow, so that's why we've already done it for you. Make sure we have the LR orbit files. That does that here, which we already have. And then here we open all the XR or HR and LR layers. We remove nadir from LR. So that's again removing the nadir, so we only have the swath coverage. And then we're reprojecting to South Polar Stereo. That's EPSG 3031. And this actually takes six minutes because there's so many SWOT paths. So that's why we started it early. So we have to do this to read in the data, and that'll be done in just a moment. And then we're going to map everything. And so in the mapping, this is where we put the grounded and the grounded ice and the ice shelves. One's in dark gray and one's in light gray. And we've chosen different colors for, so blue is LR, red is HR, or sorry, reversed. Blue is HR, red is LR. And we have some transparency just to make it nice. You don't really have to do this. And we've plotted those. And then we've added the Bach ice shelf and crop that down to 3,000 kilometers from the pole, so that is a much more manageable image. So this should pop up in just one moment. Does anyone have any questions so far? And definitely add it into the chat if you do have questions. Oh yeah, Ed Armstrong said there might be a more robust way to grab the times from the metadata. So there may be faster ways. Sweet. So we have our plot here, the ice shelves and the grounded ice and everything here. And you can see what SWOT coverage is for HR data. And we have lots of it over Bach. And one thing I wanted to note, the %matplotlib widget, what it allows us to do here is to, be able to zoom in. It'll take a second to replot that. You can save, you can move this around if you were to use that button, and then we can go back. So that's the nice thing about having Matplot, the magics, they do cool stuff like that. So now that we have data over Bach, we can see that there's coverage there we want to compare to ISET2. And just a little bit of background for ISET2, why we might want to compare ISET2 data to SWOT. And we can do this over sea ice, over land ice, and over the ocean. ISET2 is a photon counting green laser altimeter. And we can do the comparison because both SWOT and ISET2 are considered surface sensing instruments. So SWOT is Ka band radar, ISET2 is green laser. In wet snow, they penetrate nearly identically. In dry snow, there might be some differences. We haven't really tested out to see what the differences are, but we expect them to be on the order of millimeters to centimeters in the penetration. But in general, we expect them to be very close, so we can do some comparisons there. And if you want more information about and tutorials on how to use ISET2, you can go ahead and click there. So we're going to use the HR raster 100-meter spatial resolution product. So those are 100-meter pixels. And the ATL06, as I mentioned, ATL06, ISET in general ISET2 has a 17-meter round footprint. And then ATL06 averages all the photons from 40 meters into one point, and then takes segments every 20 meters. So you get about a 20-meter spatial resolution along a line. And then there's 6 tracks at the same time. So that's what we'll compare to the HR data. We're going to start by using an Earth access search mode that's slightly different from the last ones I just showed you, where you can just type in, if you know the actual granule you want, which we went and looked at Earth data search and found a really nice granule we wanted from SWOT beforehand. You can use this method for accessing it and searching for that specific granule. So we've already gone through what the learning objectives are for this section. So we can start by doing a pip install. So this is an example of using %pip install for certain things that aren't in our environment. And some of these will be updated, so we won't need these forever, but in our Python environment. But for now, let's just add them in. And as I mentioned, that's a reminder about the best practice using the pip installs. And then we'll import all of our libraries. And again, our path to all of our data that we're going to use. We're going to use the grounding line shapefile again. And this bounding box is for Bach in South Polar Stereo meters coordinates. And then the rift box, there's a rift that we're going to be looking at, a rift in the ice shelf. And so that's the bounding box around that. And then we've set up CryoPy for mapping and just pre-made some of our label sizes. We're going to log into Earth Access, but we're going to use this strategy called interactive and persist equals true. And that tells us that it will open here like it did before. And I can type that in and put in my password. Persist equals true means it's going to put it into that .netrc file. Make sure that like that .netrc file means that next time when we run it, Earth Access will look for that netrc file and won't ask you for these credentials again. Because you have that there, if your credentials change, then you'll have to go in and look for that. You can see it if you go into view for our file browser, and we can show hidden files. And if we go here, it should be the .netrc is in our home directory. It's here. If for some reason this gets put into a GitHub repository, please don't save this file to your GitHub repository because that's a huge security risk and it makes it possible for people to steal your credentials. So just make sure this never goes into your GitHub repository. So going back to where we were. So we did that login. It created the netrc file. Now we have some helper functions. These are just coordinate conversion functions from South Polar Stereo to WGS84, which is Latin long, and also from the UTM zone projection, which is what SWOT is natively in. So SWOT puts its data whatever UTM zone it is, which is different around the world. It has a different UTM zone, a different projection, and so this accounts for that and converts it all to South Polar Stereo. And then there's some color bar logic, which is just helpful for printing things, maps later. We'll load the Mosaic of Antarctica image as a base map because it's really nice looking. Here's the location of that. But what you should note here is we're going to stream this data. So we're streaming it from NSIDC, the National Snow and Ice Data Center. And this runs, you can see the star turns into a number really quickly that's opened. So that's what streaming looks like. And we didn't have to download anything. Next, we're going to get the HR data and determine ISET2 search window and search for that data in ISET2. So we're opening the HR raster data. We have a specific granule that we want to pick out because we know that it's nice. It's being opened in Earth Access into an from that object file or object format, and then it's being opened. This is something that is fairly fast right now, but Earth Access is about to release a new version that is almost instantaneous. And so the next version 15, is going to be like very fast opening of NASA data, which is really exciting. That should be released in a couple weeks. So we open the SWOT granule, then we build a bounding box to get any ISET2 data that's in that rift. So we build a square area or polygon for where that rift is. We are asking for data 9 days before and after that granule. So that's creating the time search window. And then we input that into the search in Earth Access for ATL06 data. And you can see down here, we acquired 3 files. And so then we're going to efficiently stream in. So that streamed in the SWOT data. We didn't download it and we have it now. Now we're going to stream in all of the ATL06 data that we just found from ISET2. And we have all of the different beams. Those get read in differently. We aren't going to use the same pathway that we just did. We're going to use FSspec to open up this data because it's much faster. And so we actually have to get the S3 credential to do that. So it's like basically providing you the login to be able to access that data from programming. And so in opening this, if you've used Xarray, this is like how you normally open things. We're going to use the H5 netcdf file. That's for netcdf and HDF5 file types. You have to read in them group by group. So we'll read in the land ice segments. That's going to be all of the heights. We'll read in the DEM file that's the got the geoid in it, and the geophysical has all the tide corrections and stuff. And then what you'll notice, this like block size thing that we've added here, this isn't normal to add, but this helps. This is specific to ISAT2 data. It helps speed it up. So we have people who have made this basically cloud optimized using this input. It's kind of clunky, and we're getting it put into the data. So it's baked into Earth Access. But for now, we do this, and reading this data is way faster. It's about 10 times faster when we add those keyword arguments. Then we grab each of the kinds of data that we want, latitude, longitude from all of this, and put them into their own little data pieces, including all the things that I listed for corrections. And then we mask the bad data. And then at the end here, we convert from decimal time to decimal years using the ISAT2 toolkit. And so you can see we've loaded 18 beams. So again, that's 3 passes by ISAT2, and each of them has 6 beams. So that's why we have 18 loaded. And then we want to preview these because we only want to compare one of these beams, maybe at the moment, to SWOT. We want to see which one's the nicest, which has the best data, which one has coverage of the ice shelf that we really want. So we're going to plot all of them over the SWOT swath and have the MOA context map in the background so that it looks nice. We're using the start and end here as these are indices. So 0 through 18, that's going to read in all of them. If you only want to look at a few, you can by changing those numbers. And we've color coded all of the ISAT2 beams so that you can separate them out and see which one is which based on number. So the ISAT2 index 0 through 18, you can see the purple and blue ones are the ones over this rift that we have here in the ice shelf that we can see in SWOT data. So here's the SWOT image. Here's the ISAT2 tracks that we picked out. And really only 2 of them really cross the crevasse where we want to see. And the purple one has a little bit better data. You can see this data cap here. That can happen from like clouds or something. So we want this purple one. And so we grab that index out and we will use it as we move forward, just that one beam. So that's the second track of this file here. And so you can see all the files here. So when we narrow this down to a smaller range, you can narrow down what the names are for each of those. And the middle track is ground track 2 that we're picking out. So then we're going to, because as we mentioned, there's a time difference between SWOT and the SWOT and ISAT2. ISAT2 is taken on May 15th, which is right there. SWOT was taken on May 25th. And so we need to correct for how much the ice has moved during that time. So we need to bring in the measures ice velocity data using Earth Access, streaming it in again, and apply, basically move the ISAT2 track to SWOT so that they can be comparable. So we're opening that data set and we're cropping that area to the block area. And we are going to advect using a string of different functions here. First, we're going to create this function here. This helps to prep the function for, or prep all of this for like creating a regular grid. So we have a lookup for the grid and we can efficiently find data in that grid really quickly. So it's 10 times faster than using the native grid for interpolation. So it creates this, this lookup table for the grid. Then we make a copy of the ISAT2 data so we don't change it. We apply a spatial mask down to that Bach region and get rid of all the rest of the data to make this much more efficient. And then we convert times, we get the time step, get the time difference between SWOT and ISAT2, and then we set up the time steps that this integration is going to do. Because as ice propagates, the ice in one point moves faster and ice in the next point may move slower or the opposite. And so this takes 1 day time steps and does an integration of the velocity so that we get a much more accurate propagation of that pixel from ISAT2 to the new SWOT time. And so that's just kind of integrated here, and we interpolate across those time steps. And so now we have an ISAT2 track that has been moved to where we expect it to be when the SWOT acquisition is taken. Next, make sure that I ran that. Next, we apply the geophysical corrections to SWOT and ISAT2. So one of the first things that we need to do is do a tidal correction. We use CATS 2008, the newest version that came out. ISAT2 and SWOT provide elevations. They're at different tidal heights at different times. So we have to correct for the fact that tides are different at those different times. And we model what those tides are and subtract that from the signal that we see in SWOT and ISAT2 so that we can have a fair comparison. We use CATS 2008 instead of the ones that are native in those, like SWOT uses a different one than this tide model. CATS is the best one around Antarctica because it takes into account the fact that there's ocean cavities underneath ice shelves and things like that. So it really accurately predicts models around Antarctica. So that's why we use that. And PyTMD is a Python library that runs CATS. And it can run other models as well, but we use PyTMD. And we fetch one of the files, the CATS tide model file, from an S3 bucket that one of our colleagues has publicly and puts it in the PyTMD data path. So that ends up bringing in a netcdf file that we can use. If this file ever moves out of our colleague's S3 bucket, then you can find it on USAP. You have to manually download it. It's a pain because they have this CAPTCHA function that prevents you from automating download or streaming the data. You can manually download it from there though, if you need it. And then we compute the tide corrections. And I'm gonna actually run these really quickly so that they have a second to run. So we compute the tide in 2 steps. We get all the dates and times from, the SWOT acquisition or the ISAT2 acquisition. We set up the model with PyTMD, and then we grab the major and minor constituents, tidal constituents. And that's in that function there. And then we apply this here for both SWOT and ISAT2 and put the tide corrections into our data. And then we need to think about all the other geophysical constituents. And for the version D in SWOT, we use the variable WSE, which is water surface equivalent. And that's the heights. The name doesn't really matter. The corrections just change depending on what the variable name is between LR and HR data. In LR, it's called, oh man, I don't remember what the name is. Zach, do you remember?
Sea surface height, SSH.
Yeah, SSH, that's right. Yeah. So WC and SSH, they just have slightly different corrections applied to them. So WC, we have, to get that, we get the height from SWOT minus the geoid height, minus the earth tide, solid earth tide, and load tide and pull tide corrections. So that's how we get a corrected WC. And in ISAT2, the HLI is what we're given. And to make it equivalent to SWOT, we need to remove the geoid, the mean geoid, add back the free to mean. So in the HLI product, it actually used the free to mean geoid, and SWOT uses the mean reference frame. So we need to swap those out. So that's what we're doing there. Then we need to add the tide earth correction, tide pull, and tide load. And the thing to note here is some of these corrections are kind of still in process and we're figuring some of them out, so they may change slightly. So make sure each time that you use this, you pull the updated version of the tutorial in case something has changed or we've added something. But the geophysical corrections, the products and things are evolving. So these things may change slightly in making them equivalent. And so to apply those corrections, we just do this to ISET2. And the only thing missing here are the title inputs, which we'll do in a second. And then what is really important for comparing SWOT and ISET2 is SWOT, we have a 100-meter pixel, and ISET2 has points along that. So we want to interpolate from the middle point of the SWOT raster image to those exact points for ISET2. You can do it in the opposite direction if you want, but to do exact comparisons, we want to get to that exact point in ISET2. So we do that interpolation. We convert ISET2 to the same projection as SWOT, and then we interpolate SWOT to the ISET2 points. And then we get rid of any data from ISET2 that is outside of the SWOT image. We compute the sigma, the error on SWOT data based on the WC sigma, and crop all this data again. And then we apply the title corrections. I need to make sure that I've run all of this so I don't forget while I'm talking to you. And then we plot all of it. In the plot, we have like the base map, like we talked about, the grounded ice. We have the advective points, putting that data onto the image from SWOT. And then we do the cross sections for ISET2 versus SWOT. And that's going to give us a line plot, and then we'll have the legend and stuff plot up here as well. So when we do this comparison, here's an instead of Antarctica, here's the SWOT map. The red is the area that we've cropped down to in ISET2, and you can see it's covering that rift. And then down here is the comparison that we have. So you can see the error on SWOT and ISET2 data. It looks really nice in most places. Within the rift, we see some differences based on likely the spatial resolutions that we have. But you see this nice comparison. So we've provided you with code to get this coincident SWOT HR data and ETL06. We brought them to a comparable reference and propagated them to the same location, applied the geophysical corrections, and plotted it here. So that is our tutorial. I'd love any questions about this tutorial, if you have questions about the geophysical corrections, and also about CryoCloud in general. And we welcome questions from everybody, early careers. Yeah, please feel free to open up. You can also type into the chat and we can answer from the chat if you don't want to come on screen or mention anything. And I see a question from Khalil. As I understand, this is a multi-sensor analysis between SWOT and ISET2. How do you manage this in the code? And we've talked a bit about that. How much time difference is allowed between SWOT and ISET2? Ideally minimal, but there are times we have done comparisons between an ISET2 acquisition that was a 1.5 years ago, and then you can do like time steps and whatever. So then you would be propagating over a 1.5 years, doing that like ice velocity change. And so it depends on what the application is. If you're interested in knowing like what one season is to the next, and you can see the height difference between SWOT and ISET2, then having a large time difference is fine. And you can note that, you know, there's all of the precipitation processes, like it's snowing in one season, it's melting in another season, there's compaction going on, which will make these differences. But so you can use them for both. But now that we like start to say that if they're very close in time, like we have here, which is like a few days, that we can get really nice results and they look very similar, then we can start expanding out to larger amounts of time. How much faster was it to read in the cloud optimized iSet to HDF data than the non-optimized? That it was about 10 times speed up. And it'll probably be with the new improvements to Earth access. I'm hoping that it's like even a little bit faster than that. But it should go from being like 30 seconds for a granule with iSet 2, because iSet 2 is kind of small. The way that they constructed the data was like meant to be read by a computer, like our normal laptop system. And like it's broken up to be like very small chunks. And so like how you construct your data, the data format, the compression, and the chunking size is really important for working in the cloud. And so tiny chunking sizes means that the cloud has to read them all like a lot, do a lot. Whereas if you have a large chunking size, it just needs to do one grab. And in the cloud, what's nice, cloud optimized data formats tend to allow you to grab a piece of an image instead of the entire thing. So it can grab whatever your chunking size is really easily. And you don't have to read in all the rest of the data. So that's what the lazy loading does. It gives you the metadata like structure. And then if you only use the small chunk here in the middle, you only grab that data. So that's the beauty of cloud optimized data formats. iSet 2 was built before we were using the cloud. So it was really inefficient for working in the cloud, which reads very differently than our normal systems. And so the way that we read it in with those like keyword arguments helps to speed it up. So it went from 30 seconds to maybe like half a second to read in one granule. Yeah.
Natasha, it's Ed here. Can I have one follow-up question?
Uh-huh.
Yeah, so what was the chunking size that was chosen then for the iSet granules? And what is that new feature you're referring to in Earth Access to take advantage of this chunking, if I understand it right?
I forget what the Zach, do you know what the chunking size is for iSet 2?
No, not off the top of my head. But the point is that in this new version of Earth Access is that we're not going to have to think about and figure out why that's the correct chunking size because it's going to all be done under the hood for you when you just use the default parameters.
I see. So it's going to like on the fly figure out what that chunking size is and use that to like open data, right?
It doesn't on the fly. From my understanding,
Uh,
there's two things that are being updated. One is that the data producer can put that information in so that Earth Access can like know it. So it's going to be up to the data producer to put that information in. But two, it's also using this new object-oriented library for reading in data that's really fast, from my understanding. And I don't remember what that library is. They just developed it like a week ago. So it hasn't been released yet, but it's
good.
fast.
Yeah. So is there like a structured metadata field to put that information for the data producer?
Not yet.
Uh,
That'll be coming out from Earth Access, from my understanding. They're still doing some of that work. I'm not sure if that's going to be released yet, but this new like library that they're using to open data is going to be way faster than what Earth Access currently uses for in the back end.
I know they're also working on integrating some techniques to read like data sets that have been prepared like with virtually ZAR and maybe even ice chunk.
Yeah.
So maybe that's all related. But okay. Well, thanks for answering my questions.
Yeah, no problem. And Mike mentioned it in the Slack. The new backend that's going to be reading the new library is going to be ObStore. So it works with object-oriented files really fast. Would this framework on CryoCloud be suitable for managing larger volumes of SWOT pixel cloud data? Or considering the file size, would it be more efficient to process it differently? I haven't used the pixel cloud. Tiago, do you know what size the pixel cloud data is? You can type it in if you want. Yeah, 1 gigabyte. So the data can be streamed in. So it'll be a little bit slower to read in some of this data, but 1 gigabyte is totally fine. Like when we were choosing our compute size, 32 gigabytes is what we're allowed. Or I guess it's like 29 with like all the overhead and stuff. So 29 is what's supplied. So you can read in you can stream in a lot of this data really easily. And that includes pixel cloud data. If you want to get to large file sizes, are doing a ton of that data, reading it all in at once. You might have to get creative if you're doing like more than 30 images at a time, but sometimes you can open one, do the processing, spit it out, do the next one, and then it goes really fast. And then you don't have to worry about reading in like 100 at the same time. We also, I need to note, um, we've provided every user with access to 32 gigabytes of RAM, which is 4 CPUs. There is an option for 128 gigabytes of RAM. If you need something larger, you can ask us for that and we'll give you access to that larger computer. And we also have a GPU, a small GPU, if you want to use that. So there are other options for larger compute and different kinds of compute if you do machine learning and things like that. So that's also an option. All right, so we're at the top of the hour. I hope that all of this has been really useful for you. If you have any questions about using CryoCloud, definitely use our Slack. Reach out to us individually if you want. Lots of people respond on Slack, especially the tool developers. So like we have like a lot of the tool developers sitting on Slack that you have seen tools from, including Xarray and Earth Access and things like that sitting in our Slack. So definitely ask questions there. Yeah, let us know how you're using it and do great science. Thank you, Joanna and Zach, for all of your help today.
Yeah, thanks so much everyone for being here. We can't wait to see what you all do.
Hopefully this is helpful.